Professor Sudeep Bhattacharjee is an alumni of our North Bengal University, and he has also worked in many different places abroad for his PDF and other degrees. I will tell Arindam sir to give a brief introduction about Professor Sudeep Bhattacharjee. Over to Arindam Mukherjee sir.
Thank you, Toma. Professor Sudeep Bhattacharjee is my 1 year junior in the master's degree, and to be in detail, Professor Sudeep Bhattacharjee is currently a professor in the Department of Physics at the Indian Institute of Technology, Kanpur. He obtained his MSc degree in physics from the University of North Bengal in 1992, post-MSc from the Institute of Plasma Research in Gandhinagar in 1994, and his PhD degree from the Institute of Physical and Chemical Research, Riken, Japan in 1999, in experimental plasma physics. Thereafter, he was a special postdoctoral researcher at Riken from 1999 to 2001. From 2001 to 2004, he was a postdoctoral research associate in the University of Wisconsin, Madison, USA. Since 2004, he is at the Indian Institute of Technology, Kanpur, where he became a full professor in 2014 and held the Sanjay and Rachana Pradhan Chair professorship from 2017 to 2020. Professor Bhattacharjee's research interests lies in the fundamental plasma physics and ion beams derived from the plasmas. Professor Bhattacharjee received the Booty Foundation Award for Research Excellence in Plasma Science and Technology in India in 2009 and held international fellowship such as the Japanese government Monbusho Scholarship, the Australian government's Endeavour Research Fellowship, and the Norwegian government's Specialist Exchange Fellowship. Professor Bhattacharjee has written a book titled Compact Plasma and Focused Ion Beams, published by Francis and Taylor in 2013. Welcome, Professor Bhattacharjee. I welcome Professor Bhattacharjee and request him to deliver his talk.
Thank you. Am I audible?
Yeah.
Thank you.
Yeah.
Thank you very much, Dr. Arindam Mukherjee, for asking me to deliver this colloquium. It's indeed my greatest pleasure to deliver this talk today, which has been organized by the Cosmic Ray Group of Astronomy and the High Energy and Cosmic Ray Research Center, HEC RRC, at the University of North Bengal. I must say I'm actually very much overwhelmed by all of you, particularly Professor Arindamda, and of course I saw today Arunabhada also. They were my seniors, and the love and blessings I received from them, and also from my university where I did my MSc, I think is above all. And whatever little I am doing today is because of blessings of my seniors and the university. So without further delay, I would like to deliver my presentation. The title of my presentation is Intriguing Physics of Plasmas Confined by a Dipole Magnet, from Colossal Planetary Magnetospheres to a Tabletop Plasma Device. Before I go into the talk, I would like to acknowledge my PhD students, masters, undergraduate, our funding agencies, and the physics department workshop, without whose help this work could not have been done. Let me start with a brief introduction about plasmas before I go into the main topic. Plasma, as we all know, is known as the fourth state of matter. So it can be created by raising the temperature of a substance until a reasonably high fractional ionization is obtained. Under thermodynamic equilibrium, the degree of ionization and the electron temperature are closely related by the Shah's equation, as we all know. And this is one of the most fundamental equations of plasma physics. How can plasmas be created? There are mainly two ways: photoionization, for example, ionization by absorption of incident photons, whose energy is greater than equal to U, where U is the ionization potential of the absorbing atom. U for oxygen is about 13.6. So therefore, it requires a wavelength less than 91 nanometer for ionizing oxygen atoms, which falls in the far UV region. If you use electric field like DC or RF, you can also ionize a plasma, or microwaves. Here, electrons are accelerated to high energies in the wave electric field, and they can ionize the gas. So therefore, one can have gaseous, metallic, and even solid state plasma. Now the question is, can any agglomeration of charged particles be called a plasma? Suppose I give you a collection of charged particles. Can we call it a plasma? The answer is no. So let us look at certain guidelines. So a quasi-neutral system of free electrons and ionized atoms or molecules, which exhibit collective behavior due to long-range Coulomb forces. Now, what do I mean by quasi-neutral? So it means that we can take the number density of ions almost equal to number density of electrons, and N is called the common density. So both ion density and electron density are equal, and we take it as the plasma density. The second point is the dimensions of the system, L, should be much greater than the Debye length, lambda d. So whenever you have a system, and if we see that the system size is much larger than L, that is one of the much larger than the Debye length, that is another criterion. So any local concentrations of charge or external potentials are shielded out, and therefore in a distance, shielded out in a distance much smaller than the Debye length, leaving the bulk plasma free of large electrostatic fields. So therefore, this is actually the concept of screening, and all the electric fields due to a charge are screened within the Debye length. There is another criterion. The picture of Debye shielding is only valid if there are enough particles in the charged cloud. So for it to be a statistically valid concept, and this behavior requires that the number of particles in the Debye sphere, Nd, should be much larger than 1. And this is the formula that N is the density and 4/3 pi lambda d cube is the volume of the Debye sphere. So Nd should be much greater than 1. And the last condition has to do with collisions. So in a weakly ionized gas, ordinary hydrodynamic forces rather than electromagnetic forces control the motion of the particles. However, if the plasma frequency is much, omega p tau should be much greater than 1, where tau is the mean time between collisions with neutral atoms. So basically, the plasma frequency should be much larger than the frequency between the electron and neutral collisions. And therefore, omega p decides the typical plasma time scale. Lambda d decides the length scale, and omega p decides the time scale. So to summarize, these are the 4 conditions for a collection of charged particles to be called as a plasma, as I have listed below. Now, our plasma world is actually much wider than we think. On the figure in the left-hand side, I have plotted the electron density, and in the y-axis, I have plotted the temperature. And different types of plasmas are shown in this plot. So you can see the solar core is on the top corner here. Densities and temperatures are given. The lightning, the fusion reactor, solar corona, industrial reactor, flames, aurora borealis, nebula. All these different types of plasmas are shown pictorially along with their density and temperature. Now, let us look into a little more physics. How do we classify them? So the figure on the right hand side shows different criterion or divisions inside plasmas. For example, if you look at this figure, there is relativistic plasmas, classical plasmas, strongly coupled plasmas, and quantum plasmas. Now, I will briefly tell you, if the KBT is much larger than mc square, rest mass energy, we have the relativistic plasmas. On the other hand, if the Fermi energy is much larger than KBT, which is for very high densities, we have the quantum plasmas. Then if you look at the n lambda d cube, n is the density and lambda d is the Debye length. So if n lambda d cube is much greater than 1 or much less than 1, below this dotted line, you have the Coulomb effects are much larger than the thermal effects. So you have a strongly coupled plasma regime. And if the Fermi energy is much greater than E square n to the power 1/3, then of course quantum effects are dominating over the Coulomb repulsion effects, and you have the idealistic quantum plasma. So this shows the wide applicability of plasma physics. Now, once we have created a plasma, how do we confine it? So on the left, I have shown a fusion reactor, which is a tokamak. People try to harness energy and create nuclear fusion in a tokamak. So look at the plasma picture in the bottom inside this tokamak. It is made with toroidal coils. These circular coils are called toroidal coils, and these D-shaped coils are called as the poloidal coils. So a combination of toroidal and poloidal magnetic fields creates a helical magnetic field, and that is how the plasmas are confined. Remember, plasmas are charged particles, so they have Coulomb repulsion effects. So they need to be confined by this kind of magnetic fields. On the right hand side, there is another kind of plasma device, which is a linear device. And here you have solenoids, and you can create an axially long plasma as shown in the picture below. Then in a very compact geometry, you can create a multicast magnetic field. For example, this is a magnetic bottle shown in the left, and you can see that these north-south poles are arranged alternately, and the field at the center is 0. So the plasmas are all confined. This picture shows a star-shaped feature, which is a plasma inside a multicast. And the null magnetic field at the center helps the plasma confinement, because the field increases as you go toward the wall of the magnet. Now, on the right-hand picture, we have a dipole magnetic field. So here, the blue color is actually a coil. And if you pass a current through a coil, you can create a dipole magnetic field. As you can see, this is a dipole magnetic field. So you can have a coil carrying current, and you can create a field which is a dipolar field, and that is how you can confine a plasma inside a dipolar magnetic field, and it is called as a dipole plasma. Now, the Earth's magnetosphere is a burning example of a naturally occurring dipole plasma. So one can see the picture here of the Earth. This is our Earth, and one can see these dipole magnetic fields coming out from the Earth. And look at the sun here. The solar wind comes and blasts, and then they actually go outward in this region, and there is a bow shock created here. And look at these fill lines which are actually blown away, and they extend for very long distances. And these unique radiation belts you can see in the green color, they are called as Van Allen radiation belts. So this is a very naturally occurring dipole plasma, and it makes our study all the more interesting, because such plasmas show a natural confinement in the even in our planetary magnetosphere. Now, some interesting physics can be studied. For example, interaction of the dipole plasma with the solar wind. Van Allen radiation belts, Bohr-shock physics, what happens in the Bohr-shock region, physics at the cusp. You notice that there is a polar cusp here. So high energy charged particles can penetrate through this cusp region, and this cusp physics becomes very interesting. And of course, if you go down this plasma sheet, you have a null point, and there is a X point where you can have magnetic reconnection physics, which is one of the very burning topics in plasma physics. So despite several satellite studies that have been done, people have developed large dipole plasmas in the laboratory, there are many unanswered questions. I have listed a few of them. What is the influence of plasma beta, which is ratio of the plasma pressure to the magnetic pressure? How is the global particle balance in the plasma? What about the particle density profiles? How do they look like? How does the charged particle diffuse in the plasma? How is the optical emissions from the plasma? What is the reason for alternate bright and less bright regions in terms of the local plasma emissivity? What is the reason for two radiation belts predominantly? Notice that in the Van Allen radiation belts, there are primarily two bright radiation belts. Why only two? Why not multiple radiation belts? Why predominantly two? People have reported a third belt also, but why predominantly two? How about the conductivity of the anisotropic plasma? These are some of the many unanswered questions which we have tried to look at experimentally. Now I go into the main topic. So dipole plasmas, can we live without them? As I said, dipole magnetic field structure holds together colossal plasmas in space with infinite boundaries. Planetary magnetospheres such as those of Earth and Jupiter. And they are the burning examples. And we have these Van Allen radiation belts there. Now, as I said, dipole plasmas can sustain high beta plasmas. And beta is the ratio of the plasma pressure N kBT, where N is the plasma density, Boltzmann constant temperature of the plasma, and B square by 2 mu naught is the magnetic pressure. So dipole plasmas are known to sustain very high beta plasmas. Now, this is a very unique confinement scheme. As you have seen that these kind of magnetic structures are not there. Here you have a twisted magnetic structure. A dipole confinement is a very simpler confinement. So the question is that most confinement schemes for stability requires a good curvature and magnetic shear. But dipole plasma stability is derived from plasma compressibility and utilizes the large flux tube expansion. So as you go out of the dipole, you have the flux tubes that are becoming larger and larger. And that is one very important criteria. So the adiabaticity condition, delta of PB to the power gamma greater than 0 has to be maintained, where P is the plasma pressure and V is the differential flux tube volume, and gamma is your ratio of the specific heats. So it is found that this is some kind of a stability criterion for the dipole plasma. Now, it is this adiabatic constant which decides the dipole stability. And people have proposed this dipole concept as an alternate for nuclear fusion. Now, there are exciting research opportunities, as I say, both in fundamental laboratory plasma and in space plasma. One can understand the physics of dipole plasmas. Now, topic of interest is confinement and stability, particle balance, diffusive transport, anisotropic conductivity, waves and instabilities, plasma fluctuations. These are some of the main topics of interest. Now, I will tell you about some large experiments in the world where people have tried to create such dipole plasmas. Now, look into this figure on the left. This is a levitated dipole experiment at MIT, USA. See the size of a person in green shirt below this large device. So you can see this device is really huge. And one can see this coil, superconducting coil, I will tell you, and these are the dipole magnetic field lines. On the right hand side is a ring trap experiment at the University of Tokyo. Here also you have a superconducting coil, and these are the magnetic field lines, and this is also a huge experiment. Now what they do is pass current through a superconducting ring and generate a dipole magnetic field. Now the main findings are chaotic particle transport, magnetospheric vortex formation, magnetopause measurement. People have found these things in the laboratory as well. Inward diffusion of particles leading to peaked density profiles. I will come back to this very interesting thing a little later. Experiments, however, were limited to the pulsed regime, because you can understand these are superconducting coils and there are heating issues. So because of the heating issues, people could only perform pulsed experiments. And there were also plasma accessibility issues, and space resolved measurements remained a challenge. So although they could produce a plasma, they could find some very interesting findings, but they could only carry out pulsed experiments, and they could only do very, they could not carry out very fine space resolved measurements. So what we have devised is, we have made a tabletop experiment, tabletop device, which employs a single permanent magnet to create a dipole field. And it supports creation of steady state plasmas. It's a unique low cost experiment and retains most, if not all, the basic physics of large experiments. So here is our experimental setup. I will explain to you in a while. So the left hand side is the schematic diagram of the experimental setup, and the right hand side shows a digital picture of the experimental setup that we have developed at IIT Kanpur. So let me explain to you. This is a large spherical chamber on the left hand side. You can see it's a spherical chamber, and there is a small magnet which is put in a water cooled jacket, and you can see there is a water inlet and water outlet through which we pass chilled water, because otherwise the magnet would get demagnetized due to the heat from the microwave which is used to create the plasma and the plasma radiation. So this magnet has to be kept in a water cooled condition. Now in the left hand side you have a microwave generator MWG, which generates microwaves of 2.45 gigahertz. And these microwaves are passed through an isolator which protects the magnetron. There is a directional coupler DC which measures the forward and reflected power. There is a triple stop tuner which is to impedance match the the impedance between the plasma and the generator. And then through a straight waveguide and a quartz window, the microwaves are launched into the plasma chamber. And you can put gas through a gas inlet. There's a GI, which is a gas inlet at the bottom. And then the plasma can be created by microwaves. Remember, I told you in the beginning that microwaves can be used to create a plasma. So this is how the plasma is created. And this is my dipole magnet, permanent magnet. And this is the magnetic field lines. And notice that there are several ports all around the chamber, like one at 90 degree, one at 45 degree. These are also seen in the digital picture. Through these, we do the plasma diagnostics. You can see a Langmuir probe being inserted into the plasma from here. There is another diagnostic can be inserted from here. So all these ports are utilized to put our diagnostic probes into the plasma, and you can do the plasma measurements. And this is the microwave system, as you can see, that is shown in the schematic. These are all the electronics and measurements systems. This is a computer which controls the microwave, and the whole experimental setup has been shown. This work was published in this Review of Scientific Instruments in the year 2018, and we have also patented this work. Now here is the beautiful picture of the dipole plasma. You can see this beautiful butterfly shaped plasma, and look at these bright rings. And remember, compare them with the Van Allen radiation belts, these green belts that you can see here, and you can see these bright ring-shaped structures that are formed in the dipole plasma, which radiate, and these are like similar to the Van Allen radiation belts. You can see on the left-hand side very clearly, there is a bright ring here, there is a dark ring here, again there is a bright ring here, and then this is excellent dipole, the structure bears. So let me tell you something about this plasma. So visual observations show existence of alternate bright and relatively less bright regions. Although different pressure and field intensities, the regions show structural resemblance to the Earth's Van Allen radiation belts, whose mechanisms are still not completely well understood. A characterization of the optical emissions has not been performed yet in such plasmas. So this is, now I'm going to tell you that we have done some excellent optical measurements. So let there be light. Space resolved optical emissions in this dipole plasma from inversion based experiments. Now this is the schematic. Imagine this is a cross section of the spherical chamber, and this circle here is the plasma over here, and you can see this OP2 which is the optical probe, and look at the optical fiber. This is a black color at the bottom written as OF, which is the optical fiber, and the red line is the trajectory of the optical fiber. So what you can do is you can get this yellow color dotted line is the line integrated optical intensity. So what happens is, as you move these optical fiber along the red line, the fiber is always facing the plasma in this direction, and you can get the line integrated intensity at every distance r from the center of the plasma. And this is exactly, look at this equation. So we measure the intensity, and then we do to find the local intensity, you have to do a Abel transform. So once you do an Abel inversion, you can get the local emissivity of the plasma. And this is the figure that I have drawn here. On the y-axis is the normalized local emissivity, and on the x-axis is the radial distance from the plasma. And this shaded region is the surface of the magnet. So one can see this very distinct B1 and B2 are the two bright emission belts. The radiation belts are very clearly obtained in our plasma, B1 and B2. And this Abel inversion technique was verified with several methods: direct method, 3-point deconvolution method, Hansen law method, Pretzeler method, Bell matrix. All of them are agreeing very well. All these techniques are agreeing well with our technique of with this technique of the Abel inversion. So very clearly these bright belts, radiation belts, are reproduced. Now, how do we characterize this dipole magnet? So one can see this cylindrical permanent magnet here. Remember, our dipole magnet is just a cylindrical magnet. So this is the cylindrical magnet here, and you can see different polar angle, 30, 45, all the way up to 150. So what we have done, we have taken a Hall probe and we have done very accurate measurements along all these angular directions at every r. And then if you plot, you get this nice dumbbell shaped structure, and you will get this dots, square dots are all the data, and the lines are basically the fitting. And very nicely, you can also plot with the distance, radial distance r along different directions, and you can see this 1 by r cube. So if you look at the dipole magnetic field formula, it goes as B naught by r cube 2 cos theta r cap plus sin theta theta cap. So it has both r and theta cap dependence, and this is how we can fit it, as you can see. And the value of B naught actually for a current carrying coil is like mu naught m by 4 pi. So it's a lumped constant, and you can, so ideally for a point dipole, it will be a single value. But since our magnet has a finite size, so the B naught also varies a little bit with angle, as is shown by the red colored line in this bottom figure, where I have shown with and the x-axis is the angle, and the left y-axis is the value of B naught, which is this constant here. And the blue color is the ECR position. Remember, we have launched microwaves of 2.45 gigahertz. So therefore, when the wave frequency matches the electron cyclotron frequency, we have electron cyclotron resonance. And for a wave of 2.45 gigahertz, the magnetic field required is 875 Gauss. So these blue color shows you at different polar angle where is the ECR location. On the right y-axis, you can see the distances. So we can tell exactly the ECR location where it is satisfied. And the figure on the bottom right-hand corner is a polar profile of the ECR position. So basically, you can imagine that this pink color line, you can imagine if you rotate in 3D, you get an ECR surface. So around the magnet, there is a ECR surface that is there present. Now let's look at the ratio of plasma and magnetic pressure, which I talked about, the plasma beta. So what I have plotted here, R is the distance from the center of the magnet to about 20 centimeter, which is the length of the plasma, 20 centimeter. And this around 1.35 or 1.5 centimeter is the surface of the magnet. So there is no data inside that. Now, what I have plotted is beta in percentage. And as you can see on the right hand side, beta is ratio of plasma pressure to magnetic pressure. And this table here shows values of beta at R equal to 7 centimeter and R equal to 13 centimeter. Let's look at R equal to, let's say 13 centimeter, this blue dotted line. And for 45 degree and 90 degree angle, you can see that the beta is about 0.05, and for R equal to 13 centimeter. And the percentage beta will be then 5%. So what we understand is that if we increase the power of the microwave, the density will increase and the beta can be enhanced further. We also have additional microwave heating at another frequency, and then also you can increase the density. The magnetic field, it can be lowered a little bit, and that way one can control these N and B and temperature to some extent, and we have found that we can actually even achieve beta greater than 1. So that means the local plasma pressure will be higher than the magnetic pressure. This will be a very unique confinement to study. For solar corona, beta is about 1%, just to give you some idea. So we looked more into beta and space potential to understand what defines the confinement length scale. Now, have you ever thought that the magnetosphere around our Earth, what is the plasma confinement length scale of the magnetosphere? Have you ever wondered? Is it 1,000 kilometer? It is 10,000 kilometer? How far is the plasma confined? And what is the reason of the confinement, or what decides the confinement length scale? So let us again come back to this figure. I have plotted beta in the left y-axis and the radial distance in the x-axis. In the right y-axis, I have plotted the plasma space potential. Now, what is the space potential? This is proportional to the plasma density, or you can think like this: wherever there is a higher concentration of charge, you will have a higher potential. This is from basic undergraduate physics. So the space potential Vs gives you an indication of the ability of the density or the charge accumulation. So now let's look at this. I will show you. So this is that beta in green color, which I also showed you earlier. This one, same beta, and the space potential is kind of uniform up to about 8 centimeter, and after that it decreases. This is a Boltzmann fit to the space potential. Now let us understand one more thing. So this small figure on the right hand side is the total integrated flux. How do we calculate this? Flux is given by surface integral B dot ds, and this is 2 pi B naught sine square theta naught 1 by r1 to 1 by r2, initial distance to final distance. We can calculate this integrated flux for this magnet, and you can see that after some time this tends to saturate. Look at the data here, where on the y-axis you have the integrated flux, x-axis is the radial distance, and one can see that at first the flux increases very sharply and then tends to saturate. So that means this is a unique property, that the flux, no matter how far you go, the flux, and you go on integrating the flux does not increase anymore. And look at this. This is also saturating from around 7 or 8 centimeter. Look very carefully. So this also falls in this. If you come to the left graph, this also, the integrated flux tends to saturate from about 6 or 7 centimeters in this shaded region. So therefore, all of these, the plasma beta, the space potential, and the total integrated flux of the magnet, that saturation dictates the plasma length scale, because we have found that the plasma is kind of confined up to this region where the beta, where the space potential starts to fall down. And if you look at the box in the bottom corner, here the Debye length of this plasma is about -2 to -3 centimeter. So the length scale of confinement is about 8 centimeter, and roughly you can understand 1000 lambda d. So what is the length scale of this confinement? It is about 1000 lambda d. So one needs to verify for our magnetosphere, what is lambda d and how far is 1000 lambda d? Does it agree with this quantity or not? That needs to be checked. Now here in this slide, I show you some plasma parameters. So this is the electron temperature. You can see it is hot near the surface of the magnet and decreases as we go outward. The values are ranging from about 1 to 5 eV. The ion density shows very interesting effects. So look at this, y-axis is the ion density, x-axis is the radial distance from the magnet, and these 45, 90, these are the polar angles, and 0.4, 1.2, these are the pressure of the gas in millitorr. Here also in the left hand figure, 0.4, 1.2, these are the different gas pressure in millitorr. Now coming to the density plot, we can see that a very interesting feature. Notice that, let us focus on this 90-degree data, which is this red circle. You can see that the density increases as we go from the surface of the magnet. This dotted line is the surface of the magnet, reaches a peak here, and then it goes down. So this peaked density profile is very interesting. That means there is actually inward diffusion. That means particles from the outer region are being driven inward. See, there is also an ECR region near the magnet, as you saw, but where the plasma is getting heated, but the ECR region drives particle outward. So there must be another mechanism which is driving particle inward, and therefore we get a peak in the plasma density somewhere near about 8 centimeter. And this phenomenon of ECR, this inward diffusion, has been confirmed experimentally. If you remember that in the magnetosphere also, there is a inward diffusion from the outward region of the magnetosphere, which is driving particle inward towards the inner magnetosphere. So this is a very interesting finding which has been verified in the laboratory. Now we tried to look at a global particle balance, which is like, as I mentioned, that what is the overall particle balance? This is related to the global plasma sustenance. Now here there is an equation. On the left hand side is the plasma production rate, and in the right hand side is the plasma loss rate. Now production of course happens by ionization, loss happens by diffusion and recombination. The first term is the diffusion loss. The second term is the recombination loss. So look here, alpha gamma is the recombination coefficient, Ne is the electron density, N plus is the ion density. So recombination always happens between electrons and ions. So this term is the recombination loss. And the diffusion is of course this D, which is the diffusion coefficient. And this is the electron density. Ionization happens from electron density, the gas density, and the cross sections are all here. So what we have plotted in these two figures, Z is the plasma production rate and R is of course my radial distance. And LP on the second y-axis on the right is the loss rate LP. And in the next figure, Z minus LP, that means production minus loss, which gives you the plasma retention rate, and of course with radial distance. So let me focus on the plasma retention rate because that is most important. And one can see that as you go away from the magnet, the plasma retention rate is very high until about 8 or 9 centimeter. And after that, Z minus LP becomes negative. That means the loss rate, as you go away from the magnet, the loss rate dominates. These numbers here, 1.2, 0.4, 1.22, these are actually the pressure in millitorr. And the red color, the solid lines, if you see here, solid lines are for theta equal to 90 degree, and the dashed lines are for theta equal to 45 degree. Okay, so the other important point is, if you look at these blue circles, you can see there are some regions where Z minus LP is 0. And you can see that means Z minus LP 0 means what? Production equal to loss. So we found that depending upon the pressure, the production becomes equal to loss, and it can be tuned over a wide distance. See, it can be, starting from, let's say, one region is here from about 6.5 centimeter to about 8 centimeter, you can have production equal to loss. And the another region you can have about 10 centimeter to around 13 centimeter, you can have at about 0.4 millitorr. So by tuning the pressure, you can have production equal to loss. And this figure here on the top shows that in the inset, you can see that Z minus LP has been plotted with the pressure. And one can see there is an optimum pressure where the retention rate is maximum in the plasma. Now, we need to understand, Arindamda, how much time do I have, Arindamda? Hello? Hello?
No time pressure is there. You can take 10 to 15 minutes easily.
Okay, I will finish in another 10 minutes. Okay.
Okay. Okay.
All right. Thank you.
Sir, 15 minutes.
So,
About 15 minutes.
We need,
15 minutes.
Okay. Okay. Thank you.
Easily.
Thank you. So let us try to understand the diffusion. Now, what kind of diffusion is it? Before I tell you about the diffusion, there is a diffusion process in plasmas which is called classical diffusion. So I will come into that a little later. What I have plotted here is on the left axis is the diffusion rate at 45 degree. On the right axis is diffusion rate at 90 degree. X-axis at the bottom is the magnetic field for 45 degree. X-axis at the top is the magnetic field for 90 degree. These are in Tesla, you can see here. And what I have plotted, the 45 degree data, diffusion rate for the 45 degree data is in blue squares, and diffusion rate for the 90 degree is in red circles. So we have tried to fit this diffusion rate, and we found that this fits as 1 upon b square. Now the question is, why is the diffusion classical? So in a magnetic field, normally it is expected to go as 1 upon b in conventional plasma physics. So I will tell you why is this diffusion classical, because classical, then only it will go as 1 by b square. Although it is a magnetized plasma, why is the diffusion classical? That is the big question. Now, what I have plotted here, you can see omega p by omega c. So omega c is the electron cyclotron frequency, and omega p is the plasma frequency. Remember, in the first slide, few slides, I told you it is the characteristic plasma property, which is the plasma frequency. So this ratio I have plotted on the left y-axis, and in the right y-axis, I have plotted the Larmor radius of the electrons with the Debye length of the plasma. So Larmor radius means when the electrons are circulating around the magnetic field line, the radius is called the Larmor radius, as we all know. Now let us see. So for this x-axis is the radial distance, and the dotted line is the surface of the magnet. Now you can see that for most of the regions, the omega p by omega c is given by red circle, solid circle, and solid square, and the Debye length ratio is given by triangles. So you can see for most of the region of the plasma frequency is higher than the cyclotron frequency. And also the Larmor radius, that is the radius of gyration of the electron, is higher than the Debye length. Now let me read these few points. So conventionally, diffusion across a magnetic field is considered to follow Bohm diffusion, which is this formula. So it has a 1 by b dependence, kBt divided by 16 EB. However, dipole plasma, although it is a magnetized plasma, seems to indicate a classical diffusion scaling, which is 1 by b square. Now, why is this? See, if you have omega p always greater than omega c, then it is easier for the particles to follow the classical diffusion in the weaker magnetic field region, because as the particles are going outward, they are entering the weaker magnetic field region, and the plasma frequency is higher than the cyclotron frequency. So, and also we have seen that the Larmor radius is much larger than the Debye length. So what happens is written in these 2 points: electrons gyrate and they enter substantially weaker region as they go out and collide with new particles, and therefore lose energy by the random walk phenomenon. So the classical diffusion actually is a random walk phenomenon. Now, in order to further verify that, I will request you to draw your attention in the right figure. So what I have plotted here is the electron neutral collision frequency nu c by omega c, the cyclotron frequency. And this is my x-axis, which is the distance from the magnet. So in our case, the electron neutral collision frequency is much smaller than the cyclotron frequency. So the diffusion coefficient actually is given by step length. I mean, if you look at a random walk problem, imagine you have a drunken person who is going here and there. What will be the random walk? How will you calculate diffusion for a stochastic process or a random process, for example? So you will take the step size square by the step time. So that is in our case delta square by tau. Tau is the mean collision time, and delta is of course now what is the step size? That is our Larmor radius. And what is the step time? That is the mean collision time. If you put these numbers, you actually get the diffusion coefficient coming as 1 by v square. So which shows that indeed, although it is a magnetized plasma, but because the magnetic field is a special type of magnetic field which decreases as 1 by r cube in a dipole, so it follows the classical diffusion. Now I will tell you, we further investigate this diffusion by studying the transport in this diffusion. So we developed two diffusion models, and we tried to do a modeling of the plasma density profile with specific input from experiments. So we wrote the fluid equation and the continuity equation. In model 1, we wrote both the electron and ion fluid equations, and we took the temperature from the experiment. So we obtained the ambipolar electric field self-consistently. In another work, model 2, we took only the electron equation, and the temperature and space potential we took from the experiments. Then what happens? We took the gradient of the Vs, then that will give you the ambipolar electric field here. So resulting equations are solved numerically, and they yield radial and angular plasma density profiles. And then these are compared with the density profiles measured directly from the experiments. So I am not going through the mathematics. This is like the fluid model, ion equation, electron equation, ambipolar electric field. Based upon this, you can get the radial diffusion equation, you can get the angular diffusion equation, and you can actually see here, see in the radial diffusion equation, you need this temperature. If you look very carefully, this temperature is actually provided from the experiment here also. And we can write a similar, this is only for the model 1. I'm not talking about model 2, but model 2 is also done in a similar way. And then we can plot these radial and angular profiles of plasma density. So this is the density profile. You can see on the y-axis is the density, x-axis is my radial distance. And these are M1 is shown by the model 1 with the solid lines, M2 shown by model 2. Remember, there are two models, and the theta, these experimental results are shown by the solid circles, square and triangle. And one can see these are for different angle, 0 degree, 45 degree, 90 degree, and at 0.4 millitorr pressure. One can see a beautiful agreement between, and also not only that, the most important point I have written here, the peak density profiles, especially in the mid plane, strongly suggests inward diffusion. So the inward diffusion is a natural outcome of the solution of the diffusion equation. Now here is the polar profile of the density, and in the different polar angle, as you can see, and the densities are mentioned here with the different models. So the dots and circles are showing for 0.4 millitorr, 1.2 millitorr, and 2 millitorr. And there is also a very good agreement. So what we have tried to show here is that if you write a diffusion equation, and if you solve the diffusion equation with specific inputs from the experiments, you can actually get back these density profiles. These density profiles are obtained separately by another experimental technique called Langmuir probe, and they are agreeing very well. So diffusion actually equation gives you these density profiles. And the second point is the inward diffusion, which is very counterintuitive, because normally diffusion happens from a higher density to a lower density. But it is very uncommon to find that diffusion is happening from a lower density towards a higher density. This is a very remarkable finding. I think this will be the last slide, then I will conclude. Because of lack of time, I will stop here. So the last question is adiabaticity maintained? Remember, in the first slide or so, I talked about that dipole confinement is a very unique confinement. It follows PV to the power gamma is constant. Unlike a Tokamak confinement, which are mainly following the magnetic shear and curvature and all that, here adiabaticity is very important. So what is P? P is the plasma pressure, and the V is the flux tube volume. How do you calculate V? By this, you have to take the elementary flux and then you integrate dl by B. dl is the flux line element, and if you integrate that, you can find the volume of a flux tube. And then dl by b is actually given by r d theta by b theta. And then you can actually get plot this PV to the power 5 by 3 with the radial distance. Now I want to focus your attention here. This is for 3 different pressures. So at 0.4 millitorr, which is a lower pressure, 1.2 millitorr higher pressure, and even 2 millitorr is the highest pressure. Now remember, this is a plasma which is created by electron cyclotron resonance. So there are acceleration processes in the plasma, right? Therefore, at lower pressure, which is 0.4 millitorr, these black squares here, you can see PV to the power gamma is not constant. But as you go to higher pressures, where the resonance mechanism becomes bad because of collisions in the plasma, so then you are actually this PV to the power gamma tries to become constant over the whole length of the space. So the adiabaticity condition is better maintained at higher pressure where resonance conditions are bad. So effective heating processes such as ECR can destroy adiabaticity. So I think I will conclude. I will skip these talks. I will summarize. So what I have talked about, I gave you a brief introduction to plasma physics. I talked about physical properties, flux tube expansion, plasma beta, diffusion, particle balance. I talked about adiabaticity and optical emissions. I did not get time to talk about plasma stability. I talked about plasma parameters, density, temperature, and the space potential, which has been obtained over r and theta. I have talked about particle balance, which is the global particle balance in the dipole plasma, production rate, loss rate, retention, which is mainly important, that is production minus loss, have been investigated. I studied the plasma diffusion process, and we found that although it is a magnetized plasma, but it follows the classical diffusion law in the low collision regime. That means the collision frequency smaller than the electron cyclotron frequency. Then we looked at the solution of the diffusion equation. So we solved the diffusion equation and we obtained steady state densities in r and theta. And we found that results of the two models agree quite well with experiments. I talked about adiabaticity condition, where PV to the power gamma is supposed to be a constant for dipole confinement. That is also decides the stability criterion. And we found that as we go to higher pressure, adiabaticity is better maintained, as we saw here. That higher pressure adiabaticity is getting maintained more and more. Maybe if you go to still higher, it will be a flat line here. But as you go to lower pressure, because the electron cyclotron resonance becomes more effective, so adiabaticity is disturbed. I did not get time to talk about drifts and MHD stability, so I have skipped that. I did talk about optical emissions, and I have shown you that there are indeed two bright regions in the dipole plasma, similar to our Van Allen radiation belts. I thank you very much for your kind attention. This is the plasma laboratory where you can see this spherical chamber. These are my students, PhD students, Anuj, Aisha, Sargam, and I think Sanjeev is helping them out. And this is Professor Ashil Fredriksen. She is a space plasma physicist at the University of Tromsø in Norway. So she wanted to work with us in dipole plasma experiments. So she came down to our laboratory from Norway and performed experiments in December, I think 2000, and I think 2 years back. So once again, I thank you all for your kind attention. I'll be happy to take any questions that you might have.
Thank you, Professor Sudeep Bhattacharjee. And I invite the listeners, if anyone, any question from them is there, to ask the talker. You can also put it in the chat box.
Sudeep, I have a question.
Yes,
Other
yes, please. Yes.
The query is that what is the magnetic field range that you can use in your experiment?
Okay. Thank you very much for this nice question. So let me go back to that slide where I have shown you the magnetic field. So let me go to that experiment. Uh, so this is the magnetic field profile. So you can see that this magnetic field, the maximum is about 0.15 Tesla for this particular magnet. But we have checked that you can also reduce the magnetic field as long as, see, the main plasma forming mechanism or initiation is the electron cyclotron resonance. So what we found is that because we are using this 2.45 gigahertz, for that the magnetic field for electron cyclotron resonance is 875 Gauss. See, these are the dotted lines you can see here in this right corner figure, where 875 Gauss is satisfied near the magnet. Now, if you have a magnetic field of much smaller value where you cannot get 875 Gauss, then obviously you have to reduce the wave frequency. So if you go to lower frequencies, then your ECR condition can be satisfied at a lower magnetic field. So I think that answers your question, Urnamuda.
Yeah. A related question is that
Yes.
when you study the diffusion,
Okay.
have you changed the magnetic field or you have keep the magnetic field constant?
Okay, let me go to that slide where I, maybe this one, yes. No, this one, so we did not change the magnetic field. So these magnetic fields, see, these are actually, you can think of as they are with distance. So these magnetic fields are changing because actually you are going away from the magnet.
Okay.
Okay, so basically, let's go to this figure. So imagine you are starting your measurements from near the magnet and you are going away from the magnet. So of course the magnetic field falls as 1 by r cube. So therefore the magnetic field decreases as you go outward. So that way it is changing. We are not changing the original magnet, but as you take the measurements, the magnetic field is of course different at different places.
I see. Okay. Okay, thank you.
You're most welcome.
Another related question, not on your
Yes.
but what is the status of tokamak right now? That is the magnetic confinement of plasma and also
Yes.
artificial sun.
Right. So the Tokamak Fusion is being carried out in India at IPR, Institute for Plasma Research in Gandhinagar. And they have actually one tokamak which is working, Aditya, it is called Aditya. And they have built another bigger tokamak, which is a superconducting steady state tokamak. It's called SST1. So they have got the plasma in SST1. And that is supposed to be a long pulse tokamak, meaning it will sustain the plasma for a steady state, maybe about, let's say, 100 seconds or something like that. But till now, successfully, the fusion power in India is not yet achieved. You must have heard about ITER. ITER is a bigger device, multi-country, region device, which is being constructed at Cadarache in France, and that is supposed to, give you this break-even condition. That means the amount of power you input will be less than the power output. So you are supposed to get fusion power in that bigger ITER device. It is under construction, and of course, when it will get constructed, yes.
Another question is there in the chat box.
Please. Okay. Let me.
I'm reading it. What are the extra physics information about the planetary magnetosphere we get from the experiment?
Thank you. This is a very interesting question. Now, let me first go to this planetary magnetosphere, this slide. So you can see these radiation belts, first of all. The extra work, so we were trying to understand why only 2 belts. Now, this is a very intriguing question, that why not say 5 belts? Why not 7 belts? People have, in a Physics Today article, they have reported that they sometimes observe a 3rd belt also, but it is very rare. Most of the time it is 2 belts. And we also find in our plasma that there is this 2 belt kind of structure if you look very carefully, and also proved in our optical, very careful optical measurements. These are done with a very specially designed, sophisticated optical technique probe. And these also gave these 2 bright belts. So it is very interesting. Now, if you ask me, what is the reason for only 2 belts? I again have to tell you that it belongs to one of those unanswered questions. We are trying to find out the reason. So out of these unanswered questions, I have tried to answer the first, the second, the third, the diffusion, inward diffusion. So very interesting. That is also present in the magnetosphere, and we have verified that. Optical emission, but I don't know the reason. So this last but one, that is still unanswered. What is the reason? And the conductivity we are working on. So there are several things, I am also going to investigate cusp physics. Aurora in the lab. We are trying to create aurora in our lab. Aurora borealis. Can it be possible? We are trying to inject energetic beam to mimic the solar wind. All these are in plants. These are the physics at the cusps. This is very interesting. This cusp physics, which was very difficult with satellite. Satellite observations very difficult, but we can very nicely do these experiments in our lab. Then magnetic reconnection. So if you look at these lines, this figure, if you extend it to the right, there is a reconnection region where the magnetic field lines cross each other. That has not been studied so much in these dipole plasmas. So we do have in mind to look at reconnection physics. So there are many possibilities. Other students are trying to look at, for example, in this, let me go to that last slide where I showed you the device. Yeah, here. So we have in mind that we will put different antennas and try to generate, try to measure the waves. People have reported Whistler waves. There are Hiss waves, chorus waves. These are all produced inside a magnetosphere. So magnetosphere, people have found that, but we want to verify them, whether such waves in the magnetosphere can be actually observed and characterized in more detail or not. Thank you. Hope that answers some of your questions.
Any more question? Is there no more question? Then we give a big hand to our talker, Professor Sudeep Bhattacharjee, for delivering an illuminating talk. Thank you. Thank you very much, Sudeep.
Thank you. Yeah. Thank you, Arindamda. Thank you very much.
And I welcome all the participants here who joined us to listen to the program. Thank you very much. Thank you to all. And with this, we end this session, and we hope we meet in the next session with a new talk.